All right. Hello, everyone, and welcome to episode number 9 of Learning Golang from Zero. This week, we have a pretty exciting topic, I think, which is concurrency. Concurrency is a pretty interesting topic because it's super relevant to programming these days as computers of all kinds tend to have more and more processors or more cores and more ability to execute tasks independently. So I think especially over the last couple decades, programmers have had to update their programming methods in order to be able to use the additional processors from that are now available in the hardware. So concurrent and parallel programming are both really useful tools and probably worth just discussing concurrent versus parallel programming. So concurrent programming is when you're dealing with multiple different tasks over the same period of time. So you don't necessarily need to be exactly doing two things at the exact same time. And I think an example of this could be like perhaps drinking tea while eating a biscuit. You're not literally putting the tea and the biscuit into your mouth, at the exact same time, but at the same time, you're overlapping, consuming those two things with each other. So you can actually even have concurrency in a system that doesn't have parallelism. So even if you only have one processor, you might want to still use concurrency because there's lots of good reasons to work on multiple tasks at the same time. One of the big reasons is you can be working on a task and then, for example, maybe you need to fetch something from the internet, let's say. So while you're fetching that from the internet, ideally, you don't want the processor to be just sitting around doing nothing. So if you use concurrent programming, what you could do is essentially put in the request to get something over the network. And then while that is happening, you might be able to use the processor to do something else useful. So concurrency is really handy even if you don't have parallelism, but it's also especially handy if you have parallelism to use. I would say these days, any server is going to have a lot of processors. So if you're writing a server application, you really want to use all those processors. One thing that I would love to hear for people who are tuning in, is it possible to have parallelism without concurrency? I would definitely like to hear opinions on this one. I have my own answer, but I'd like to kind of hear if people have any suggestions on this one. So to be clear, I definitely would say that you can have concurrency without parallelism because you can use concurrent programming on even a single processor architecture. So, and we're going to be, I think another thing about concurrency is it's really, really easy to make mistakes. And there's a lot of interesting solutions to try and keep people from accidentally making mistakes. So we're going to learn today about how Golang does that. And so I just poured myself some more tea. For today's tea, this is a Qingxin cultivar grown at 1,400 meters of altitude, 10% oxidation, slowly roasted for 60 hours. And this is a double red oolong here. I've got the whole spec sheet. Flavors of cognac, burnt caramel, tropical fruit. Seems pretty good. I'm gonna have a taste in a moment. I'm still finishing my previous tea. So yeah, let's go ahead and dive into some concurrency stuff. Oh, by the way, so for concurrency without parallelism, I would say, for parallelism without concurrency, to me, that concept doesn't really make that much sense to me. But I did read a blog post on Medium that said you could have parallelism without concurrency. I don't totally understand. It may be just more of like a semantic distinction anyways. So perhaps not the most meaningful question to ask. But it's nice to always talk about things consistently. So a colleague has, oh, by the way, we're using this book, Learn Go with Tests by the user Qui from GitHub. And it has both exercises and information for us. So a colleague has written a function that checks the status of a list of URLs. Let's take a look at this. So they've declared a type alias here. Cool. So what we know is website checker is basically a function that takes a string as an input and produces a Boolean as an output. What's interesting here, I don't think we've used a function as a type alias before. This almost seems like it's overlapping with the use of an interface. Curious for people who are tuning in, are you already familiar with Golang? Or if not, what other languages are you coming from? For me, previously, mostly Rust, Python, and Java. Oh, and Scala. But Scala is like, it's kind of similar to Java. So check websites. Okay. This takes a website checker as an input and produces a map from string keys and Boolean values. Juan Maestro 9000 says IT technician here, so no programming languages. Well, I think Golang could be a pretty good first language. I'd be curious to hear your thoughts, but hopefully, I think that Golang it seems pretty easy to pick up. So what are we doing in this function? We're going to make a new map, which this is like what we're going to later return. Great. I feel like there's actually a way that you can actually name your return value in Golang, which is an interesting and uncommon feature, I think. But they don't seem to be using that in this function. So then what we're doing, we're running a for loop and we are fetching every URL. Okay, that seems straightforward. mrubio166 says Erlang and Elixir mainly for me. Can you like remind me, is Elixir, is that running on, is it like Ruby on the Erlang VM or something like that? I've heard of Elixir and it sounds like, I remember thinking it was interesting, but I don't remember almost anything about it. So what you'll notice here, I think they'll probably tell us, is that we are doing each website check in serial, which is the opposite of parallel. So we're checking websites one by one. This is probably not that efficient because we actually could be checking all of the websites, or maybe not all, but maybe many of the websites at once. So we'll spend most of our time waiting around in this code probably for no reason. So you have to pass in a website checker, which takes a single URL and returns a Boolean. Okay. And we're doing a dependency injection so that we can test this without having to make real HTTP calls. I like that too, because we can, for example, if we're on a plane or something without internet, then we can still develop. That's really nice. mrubio166, what do you like about Elixir? I'd be curious to hear like what kind of programmer should think about learning Elixir. So here's the test. Okay, let's see. This will check for the URL. I don't quite understand. I guess it will just like return some, like this is a real URL or something like that. Like it's pretending to hit the website or try to hit the website. And one thing we have to do here is we actually need to do a deep equal. I think that's because we're checking map equality. It seems a little weird to not, it seems a little weird for like this reflect.deep equal to be the default way to do that, but I guess it's good to, it helps to inform the programmer that you're doing something more expensive than just like checking if like 2 equals X or something. Like you have to actually go through the entire map. So, okay, your colleague has started to get complaints that the function is slow. So they've asked you to help speed it up. All right. So step 1, as usual, I'm going to make a new package. And I'm going to copy paste the code. This thing is going to be called concurrency.go. I think. Yeah. And now we need to copy also the test. So let's do that. Keep forgetting if test goes at the start or the end of the name of the file. It goes at the end. Okay, so I did it wrong. So they should be called concurrency test. Is anyone on the stream already familiar with concurrent programming? I've definitely done concurrency in a lot of it in Java and definitely a decent amount in Rust. In Python, concurrency is a little weird because it's not really built into Python. So you have to like run multiple Python processes, and it can be a little bit tough to get that working because Python really wasn't designed from the ground up with concurrency in mind. So we're actually going to test the speed of check websites. Okay. That's a cool idea. So do I want to put this perhaps in, I think I want to put this in concurrency test.go. Oh, I double copied some of this stuff. So I'm going to need reflect testing, and then I'll also need time. And this might work. So to run this, I should be able to just do go test dash bench equals dot. Okay. So I remember we did benchmarking a while ago, but I haven't practiced it since then. So I don't remember too much about it. But what it's saying here is it's saying that each operation takes 225. Oh, no, sorry. Okay, each operation takes, I think this is 2.2 seconds. Let's see if that makes sense. So this is 2.2 billion nanoseconds. I think that should be 2.2 seconds. So we're gonna look at this. We're making 100 URLs, and each time we're sleeping for 20 milliseconds. So 20 milliseconds times 100 That's 2,000 milliseconds. So it makes sense that this thing is taking about 2.2 seconds because we're doing each of these 20 millisecond calls in sequence. Right, and this looks pretty similar to the number they got. Of course, we don't expect the exact number because, different little random things can affect how fast the code runs. And we don't necessarily, it would be a little crazy if it actually took the exact same number of nanoseconds. It could have to do with other programs running on the computer. It could have to do with the actual, how powerful the computer is. So yeah, that number is always going to be random. And if we run it again, we'll certainly see a different result. So yeah, this time it took 2.28 seconds. Great. So as always, when we have let's run a test here. Make sure that works. As always, I'd like to do a Git commit when I am when I have the tests passing. Oops. What I forgot to do was add the files. So Git gave me this message. What did it say? It said nothing added to commit, but untracked files present. That's a nice error message. Okay, so this book explains concurrency. I made a cup of tea. I put the kettle on, and then while I was waiting for it to boil, I got the milk out of the fridge, got the tea out of the cupboard, found my favorite mug, put the tea bag into the cup, and then when the kettle had boiled, I put the water in the cup. And you didn't just put the kettle on and stand there staring at it until it boiled, then do everything else. Okay, I'm curious. Yeah, do people find concurrency and parallelism easy to understand, or are those concepts a little bit tricky? Note that they're actually not talking about parallelism directly here. I don't think that's has been mentioned, but it's something that I kind of added in because I feel like concurrency and parallelism often kind of go together. Okay. So yeah, I think we understand why this is going to go faster. Let's see if we can do it. Okay, so when we call a function, it's blocking. An operation that does not block in Go will run in a separate process called a goroutine. Curious if there's any experts here, but I would not have called a goroutine a process. Perhaps that's just a semantic thing. When I think of a process, I think of something that's being run by the operating system. Could be just a semantic thing, but I would have called a goroutine maybe a green thread. A green thread being it's a virtual thread implemented by the Go runtime that is it's implemented by the Go runtime, and it's a lot more lightweight than spinning up an operating system thread. So the cool thing about goroutines, we can probably get more into this in a future episode, but the idea is that switching between goroutines is really, really quick, whereas switching between operating system threads can take a little while. Viega says, yes, it's an internal thing to the runtime. I'm curious, would you call a goroutine as running in a separate process? So, okay, this is kind of an epic code change because all we're doing to this code is making this one tiny, tiny edit. If you want to make code run in parallel in Java, it's it's definitely a lot more work. You have to like instantiate a new like thread pool or something, and then like create new threads and call like thread.start, and then like wait for thread to finish. Viega says no, not really. Okay. So, but in Golang, we basically all we have to do is write Go, and I mean, is that good or is that bad? I would say it seems pretty cool because we've just like made this 10-second code change to transform a non-concurrent program into a concurrent one. Now, I actually, oh, so they actually wanted this in, check websites, which is right, that's in the production code. Now, I have a question here, which I actually don't know the answer to. I don't know if anybody does, but does this function wait until all the Go routines have exited in order to return? I would say I didn't think that it did that. So it's like, how do we know that all of the results are ready? Because what happens if it just starts all of these? What if it starts all of the Go routines, but then the function returns first? Are we going to get an incomplete value back? And right, so this little thing here is an anonymous function, as they're pointing out, which is, I think it's a nice syntax. Yeah. So I'm not sure what this code is going to do, but I feel like it's not going to do the right thing because I feel like the function is going to exit before the Go routines finish. So each iteration of the loop will start a new Go routine. But when we run Go test, oh, okay. So this is actually the problem that I thought would happen, which is the function has returned before any of these Go routines finish. So it kind of kicked the routines off in the background. So we might be able to keep running the test until it passes because perhaps the Go routines will run quickly enough. I don't know. I think sometimes that would work, but maybe not in this case. So we need to make sure that we're doing this correctly. Fortunately, the test did catch the problem, so that's nice. To fix this, we can just wait while all the Go routines do their work and then return. 2 seconds ought to do it. Yeah, so this is a little sketchy. Yeah, we could wait for 2 seconds. I mean, how does that really help? Don't do this your code. You really don't want to like try and guess how long your concurrent tasks are going to take because that time might be variable. A great example of this is like, yeah, so like sometimes these things do, the amount of time it takes may be random a little bit. So, maybe it'll depend on how many, maybe it'll depend on how many different websites we need to check. That would be pretty gnarly. So don't actually do this. So we got import time here, right? Ooh. Ooh. Oh, yuck. Did I make a mistake in the implementation here? Or is it really, I don't think that I did. I want to say, I believe we mentioned this on the stream previously, but I don't think that the Golang map supports concurrency by default. So what it's saying here is that we're actually trying to concurrently write into the map from two different processes. And I think, I mean, as things go, this is not the worst problem to have. I think an even worse problem would be if you tried to write into the map concurrently from different processes and it just failed in some crazy idiosyncratic way. I believe in Java that can happen if you try to write into some data structure that's not ready for concurrency. You might actually just get like the wrong data in your data structure, which is really hard to debug. Let's try running the test again. Oh. Are we going to get the same error? Okay, so this is another crazy thing about concurrency. I didn't change the program at all, and I ran the test twice and got two different results. So that's hard because when you're debugging a program, you want to be able to reproduce the problem first. But if you're dealing with a concurrency issue, like I would call this a race condition, it's your code can produce different results each time you run it just because of the randomness of how long certain operations take. So this kind of thing is really tough to figure out, I would say. But yeah, so we got the same. I think they should have mentioned here that it's actually possible to get two different errors, but we were able to reproduce their error. So what happened? So this, we only have one element in the map. Oh, yes. So we've been snared by a classic Golang trap. The issue here is that when you're doing a for loop in Golang, what you're actually getting for this URL variable is a pointer that is updated. So the value of URL keeps changing, and we're only actually getting the newest value of URL for each of the Go routines. How do they explain this? Each of the Go routines, so the Go routines, this is a good explanation. The Go routines all have a reference to the same URL variable. So they're all writing to URL. They're going to, okay, there's actually another way that you can fix this, but I think their solution is good. So they're essentially what they're doing is they're like rebinding. They're not rebinding it. I guess they're just creating a new variable inside of the function. And then they're passing URL into their func. So now each of the functions is going to have its own value of this U variable. So that should fix this. I'm interested about this concurrent write issue, though. I think we really should be doing a. You really should use a concurrent map for this. So I don't know. This seems like a little sketchy. Does anybody have like? Is there some reason that it's okay to do this? I feel like we should not be trying to use a concurrent map with Go functions. Possibly we would want to open an issue on the book or something like this. Maybe we could actually write into, maybe if we could write into a slice or something like that, or like write into an array. And that way we could be sure that we're not creating any race conditions. I would love to hear, like, is this, well, I mean, clearly this code is not good because we got this fatal error concurrent map rights. So how do we take this and make it work? So this is, so we added a new parameter. Now it says, if you're lucky, you'll get a pass. So let's run the test. Oh, crap. We got another fatal error. Oh man, this code is a mess. Yeah, this is a great example of concurrency gone horribly wrong. We have a fatal error. We've got this different possible error where the result can be different. And apparently it's also possible for the function to pass. So I use this little repeat thing that's built into my shell, which is zeesh. And this just runs a command a bunch of times. I actually do use this repeat command at work for trying to debug race conditions, and it's been kind of helpful. Just like hammering a function until you can reproduce an uncommon bug. It's definitely a strategy. So I actually can't get this. Oh yeah, okay, cool. So they do mention this concurrent map issue. So yeah, we got a race condition. Let's use the Go race detector. Go test dash race. Oh, look at this warning data race. I love this. This is just like such a great error message. All caps. Yay. I love that. So we were able to detect the race. Let's actually maybe look at this a little bit. Oof. So read at, and then this is a memory address. And it says by go routine 8. And then they say there's a previous write by go routine 7. So each go routine, we're giving it a little number to identify it. And then they actually tell us when these or where these go routines were created. I like that because it'll make it easier to debug. And we've also got a separate data race for this other memory location between go routines 10 and 8. We've got a third data race between go routines 7 and 9 at yet another memory location, I think. Okay, and we got a fourth. So we just have like this, there's just like a ton of different issues here. Fair enough. So the data race, this one says it's a write and a write. In mine, it looks like it's a read and a write. Nope, this one is actually two writes. So you could have a data race from a write and another write, or you could have it from a write and a read. I don't think you should be able to have a data race just from two reads. It should be totally fine to read the same memory from as many places as you want without problems. On top of that, we can see the line where the code is happening. Okay, cool. So I need to take a quick break and grab some more water, but I'm going to be back in a second, and then we're going to look at. So essentially, we've created this horrendous issue, and now we need to fix it, which I think fixing it will be the important thing. So I'm going to take like a 2-minute break here, and then we can go turn on some channels and figure out how to fix this data race. All right. Thanks for sticking around and back with more water. So where are we right now? We've created a horrendous race condition by trying to write to a Golang map from multiple different Go routines. And we now need to figure out how to fix that. For anybody in the chat, have you debugged or caused concurrency bugs in your work? I would say I'm sure that I've definitely caused concurrency bugs. One of the actual, it's kind of a concurrency bug, but in one of the interesting things that I did was I was using Postgres at work, and the default level of serializability in Postgres, is it called serializable? I think it's called that. It actually the transactions can do some slightly weird things in Postgres. That would be an interesting. I'm sure Cockroach has content on this, but I was using Postgres on the default settings, and trying to like insert a ton of items, and occasionally I would get these weird issues because the transactions were not actually like as they were not as isolated as I thought they were. So it ended up that choosing a different, like just like adjusting the Postgres settings fixed that issue. Obviously, of course, Cockroach DB, uses a higher level of serializability that would fix that issue. Oh, this tea is really good. Wow. It does taste a little bit like mango, maybe. So we need to communicate between our different Go routines now. Okay. Channels are a Go data structure that can both receive and send values. Sure. I will say I actually don't really like channels as a concept. I think that they're too low level for a lot of problems. I would rather use higher level things, which we could definitely cover in a future episode. Potentially weight groups and error groups in Golang are pretty cool, and I think they do use channels under the hood. So what are we doing here? We're making a new type, which is a result. It's a string and a Boolean. I'm guessing this is a key value pair. Viega says, I've caused deadlocks because of a wonky design, but data races you can usually avoid by having some test coverage and run with go test -race. Ooh. That would be good. I'm not sure if I think I'm a little bit less optimistic about good test coverage and running with go test -race, just because if you have like a complex application, well, I don't mean to be dismissive about like, I don't want to like gatekeep and be like, oh, like, like Cockroach is so complex, our problems are so intense, and we're like struggling against the bounds of engineering or whatever. But I would say, I've definitely found it hard to figure out some data races. One thing that's like an example of things that have been tough is like some of our integration tests will take a while to run because, they might actually, use Kubernetes, or they might create resources in the cloud provider. So reproducing a bug can be a little bit tough sometimes, just because, if the test takes like 10 minutes to run or something like that, then you need to run it a ton of times, and it might be hard to do that. But yeah, we do use the race detector for cockroach DB. And I do think that that catches a decent number of bugs, which is pretty neat. So let's go ahead and try and fix this code. Oh, should I do a Git commit? I think that I made some changes, right? Well, do I really want to commit the broken code? Probably not. I would say let's not commit the broken code. You could, though. I don't know. Result channel. Okay, so what are we doing here? We're creating a new variable. And that's actually interesting. So chan is a keyword in Go. That means that channels are like built extremely low level right into Golang. So result, okay, and now we're not directly assigning to the map anymore. We're sending data over a channel. And I would say perhaps people in the comments can think of different architectures for this. One thing that you could do is one thing that actually I might suggest, it would require an external library, but what if you just used a concurrent map? Then you wouldn't actually have to change the architecture or organization of the code at all. So, okay, now we've got another for loop. This one looks a little complicated. What is going on here? So we're looping over all the URLs, and okay, r colon equals and then left arrow result channel. It looks like we're trying to like grab a result channel out of, we're trying to grab a value out of the result channel and then save it into our map. Viega says you can use sync.map. Oh, you're saying there's already a concurrent map in Golang. That seems easier. That seems, frankly, for this problem, probably a better better solution. But I think it's, we also need to learn how to use channels, and that map is probably, I would guess the map is not too hard to use. So this is interesting. I've never seen this. So we actually have a struct with a string and a bool, and we're just referring to the fields as r.string and r.bool. I feel like we did not cover this in a previous session. It's pretty interesting though. So, there is kind of some magic going on here, right? Because we're sending every value over into, so I assume this puts the value into the channel. That's great. But then this thing must actually be, it's sitting around and it's actually waiting for values. And we know that we're just like continually like listening to the channel. And then once we've like received the correct number of values from the channel, we know that our function is done. Now, yeah, so we need to make sure that we put in exactly the correct number of values to the channel, which I think we'll do that. So we've got this struct with anonymous values. I probably would have called them key and value or something, but I like the anonymous struct too. This is called a send statement. Okay, so we put a channel on the left and a value on the right. The channel is now on the right, and then this is a receive expression. Cool. So the reason that this is now safe is because we're only writing into the map results from the current process or the current Go routine. What do you call this thing? Maybe a Go routine. I don't know. But we're only writing into results from one place instead of from multiple different Go routines. And the idea here is like this function is probably like the WC function is what's expensive. And the idea is that sending a value over the channel is like sending it into the channel is really cheap. Pulling it out of the channel is probably also really cheap. And then just setting the value in the map is also cheap. So all of this, we've offloaded the heavy work into other Go routines. And we're now doing the quick work in the current Go routine. So, okay. Ooh. So let's do the test. And hopefully I'm in trouble for importing time and not using it. Interesting that that's an error by default in Go. I kind of like it. So this looks, so this looks a lot faster. This is only 23 million nanoseconds, which is 0.02. So yeah, about 100 times as fast. And the reason that it's 100 times as fast is because instead of doing 100 different sleeps in sequence, we're doing 100 different sleeps in parallel. So it makes sense. We're actually doing all those sleeps at the same time. So yeah, let's wrap this up. We actually have some more cockroach streaming content coming up in just 10 minutes with Citadel. So I'm going to be wrapping up in order to let them on, but it looks like we're also pretty done with this. So we learned about Go routines, anonymous functions. Yeah, so we can actually take a look at this. The Go routine is kicked off by using this Go. The anonymous function is this thing where we have this func, but we don't actually give the func a name. We just call it directly with the Go routine. We learned about channels. We're sending data into the channel here, and we're receiving data from the channel here. And the race detector, which we ran with go test-race. And if we run that now, it shouldn't detect any problems because the code is now concurrency safe. So this is actually like make concurrent. All right, so they're saying a formulation of agile software, make it work, make it right, make it fast. I've never heard this, but that's kind of cool. So they're saying, I think this is a little confusing because right is like, they don't mean right in the sense of like the code's behavior is correct. I feel like they mean right in more like a more moral sense or something. So they mean right as in like well factored. And then make it fast last. I really like this because yeah, this is obviously a classic programming quote. Premature optimization is the root of all evil. Like people will, sacrifice clarity in their code to try and make it faster. And I think that that's a really good point. So what are we going to be learning about next? We've got this select, which is another kind of built-in Go core primitive. And I think it's going to be like kind of a more advanced way to work with channels. So that should be a pretty interesting thing. Basically, I think we're probably going to be doing more concurrency essentially. And I definitely am looking forward to, oh yeah, we've got also this sync. So we've got actually a lot of concurrency coming up, which I personally find really interesting and I think it's a really challenging domain to work with. So thanks so much for tuning in, Viega. Thanks for the help and the advice. And I hope to see you next week for learning about select in Golang.